Thanks for stopping by our poster. I'm Veronica, and I'm going to briefly walk you through the highlights of our research and where you can locate all of the key information. Our motivating research question is how effective fault complexities, such as restraining bends, are at stopping earthquakes. This question is really important for constraining rupture length, which scales with seismic hazard. Because detailed maps of earthquake rupture traces are limited to the past few hundred years, we use Quaternary slip rate gradients to determine the long-term efficacy of geometric complexities as rupture barriers. Numerical models, such as the example shown here, enhance our understanding of the mechanics of rupture stopping by allowing us to test different factors that aren't readily accessible from the superficial rock record, such as fault strength and rupture directivity and speed. However, most numerical models aren't three-dimensional and don't include important features of real fault systems, such as complex dipping faults or non-uniform initial stress fields. This study seeks to demonstrate how these factors might impact our understanding of through-going rupture behavior of a complex restraining bend along the Altyn Tagh fault in northwest China. For anyone not familiar with this aspect of earthquake science, note that we've included important terminology for understanding the theories discussed in this poster. Our field area is the Akatengneng Shan earthquake gate, one of 4 fault complexities located along the central span of the Altyn Tagh fault. We're specifically interested in the impact of a restraining bend located within this complex region on the mechanics of through-going rupture. We've undertaken detailed bedrock mapping and Quaternary slip rate analyses to determine fault orientation, kinematics, and deformation partitioning within the field area, and we include some of the most important geologic observations here on the lower left-hand side of the poster. If you're really interested in the geologic observations, get in touch with me and I'll happily show you a detailed bedrock map of the restraining bend itself. In order to understand the mechanical conditions for fault rupture through this bend, we simplify the geometry of the Akatengneng Shan into 10 simplified fault sections based on strike, dip, and general kinematics. Using these fault geometries, we model 3 uniform stress fields to see whether any of them allow for the kinematic observations we've recorded. We test compatibility of our observations with the prescribed stress conditions using more circle analyses, which tell us about likely fault strength, and check that the fault kinematics are consistent by plotting the predicted rake of the simplified faults. We include the results of 3 uniform stress models. The major takeaway messages are given in the upper right corner of the poster, but the big result is that no uniform stress field will satisfy all of our geologic observations. This is important because in most numerical models, a uniform initial stress field is applied. We present 2 possibilities for why this might be the case, both of which are equally important. We suggest first that the stress field at the fault core must be rotated relative to that of the surrounding crustal volume. A rotated stress field would allow for all of the faults to experience different stress conditions, allowing for all the kinematics we've recorded in the field to coexist. By invoking a weak fault model, we can also explain the substantial deformation partitioning we observe in the field. Second, we suggest that stress residuals due to prior earthquakes allow for through-going rupture and demonstrate this using a Coulomb model. Both the weak fault model and the impact of prior ruptures are critical for allowing through-going rupture of this bend. That's a quick introduction to our work. If you have any questions, please reach out. My email and Twitter handle are given here, and I'll be around all meeting. Thanks for listening.